We're going to talk a little bit about some research that we did and how that impacts non-destructive inspection. We're going to talk primarily about metallic structures. We apologize for those who are we're looking for something on resin-based composites. And we're going to talk about some different topics that we think will be of great benefit for you guys tonight. So the topic is kind of fancy, and we as engineers kind of have we get a real thrill out of writing fancy topics for our presentations. But we're going to talk about some beta corrections, and we'll tell you what those are, and how we derive some beta corrections to modify some simplistic fatigue crack growth models to take advantage of a process called cold expansion at holes. Okay, so that's what we're going to talk about, and then its implication in non-destructive inspection. So next slide. Here's just a brief outline and agenda of what we're going to talk about. Some of the big things we'll talk about: the epistemology of the United States Air Force's current structural integrity program. We'll give you some introduction, some intro on linear elastic fracture mechanics and fatigue. It'll provide a good basis to the research that we did. It's kind of essential that we get a good foundation in that. Then we'll talk about the United States Air Force's structural integrity program, their aircraft structural integrity program, and how that program impacts non-destructive inspection. One of the three main legs of that program is non-destructive inspection. So it's important that we talk about that tonight. We'll talk about the research that we did, some of our data processing results, and then what we really enjoy, we're going to show some really great pictures of cracks and things. So that's something that we really enjoy. And then we'll give you some conclusions. Next slide. Okay, so Robert and I, and it's possible that the vast majority of the Hill Air Force Base individuals that you see here, not including our beautiful spouses, we wish they were engineers, but it doesn't seem to work out that way all the time, work on the A-10 aircraft. The A-10 was, next slide. The A-10, oh, look at that, man. The A-10 was originally designed in 1967 and was designed primarily around a gun. Okay, that's kind of unique. We have an individual in here that's a real big hunter. She likes guns, but I don't think she's ever seen a gun quite this big. The gun, as you can see here, is called a GAU-8 Gatling gun. It shoots 30mm rounds, and it shoots them about 65 a second. So this aircraft was designed around a gun. Some airplanes, Dr. Jones works on an airplane that was designed to pull 9Gs. Well, the airplane that we work on doesn't pull 9Gs, but it can shred up a tank pretty quickly. Some of those rounds, they put incendiary rounds, so they're hot rounds that go in and can melt through a tank and really do some amazing things. Matter of fact, we'll show you a quick video on some of these things on the A-10. Go ahead, Bob.
It's really old, too. 1970s. It's good stuff.
Easy.
For a video.
Can everybody hear it?
The sophisticated anti-aircraft weaponry characteristic of the modern battlefield is creating an increasingly challenging environment, threatening the survivability of present-day aircraft. How to defeat a massive onslaught by enemy armor, supported by mobile anti-aircraft and surface-to-air missiles, is a major concern. Anti-armor, ground-attack aircraft that can swiftly mount countermeasures and suppress these weapons and survive their punishment to deliver a lethal counterattack. The United States Air Force has determined that the answer is the A-10. From initial Air Force requirement to production, it has been fashioned with one mission in mind: close air support. From nose to tail, from titanium cockpit armor to fire suppressive fuel tanks, the A-10 is the first tactical aircraft specifically developed to deliver firepower in support of friendly ground forces. The A-10 happens to be the only airplane that will do the job. There is not another aircraft, single or in combination, that can do the close air support mission like the A-10. And with capability to loiter up to 3 hours over the battle area, the A-10 can respond immediately to the needs of the ground commander and then strike again. And again until the job is done. This combination of survivability, long loiter on station, and payload flexibility provides the infantry commander with a close air support capability unmatched in the history of tactical aviation. Ordnance, whatever is necessary to do the job. The A-10 can carry 26 Mark 82 shown, or 22 750-pound Mark 117. A typical payload may consist of 12 anti-tank Lockeye bomb dispensers, 6 electro-optical guided missiles, 2 precision-guided bombs, plus enough 30mm armor-piercing ammunition for 11 tank-killing attacks. And with a broad mix of weapons, the A-10 still has 4 stations reserved for countermeasures needed to suppress and evade enemy defenses. Whatever you're looking for in an effective ground attack aircraft, short takeoff and landing, pilot safety, diversified firepower, responsiveness and maneuverability, structural integrity, simplicity of design, economy of production, low-cost maintenance and operation, they're all wrapped up right here in the one airplane that was developed and built to be there when needed, with what is needed, the A-10.
Well, we could talk all night about about airplanes, but we won't do that. So I'd like to talk a little bit about how we sustain these aircraft, the evolution of kind of how we got to where we are right now as far as sustaining the structural integrity of these airplanes, not only the ones that were built in, say, 1967 or 1973, but we have airplanes in the United States Air Force inventory that were built and 3 generations of pilots have been flying them. So that means a grandfather, a father, and a son have all flown the same aircraft. So we have a real challenge in being able to sustain the structural integrity of our airplanes. So we have a bit of an evolution of that. As we started building airplanes, as we built them during World War II, we built aircraft with an ultimate strength mindset. Make them stout out of things we know a lot about. Well, we had some problems when we did it that way. We had some accidents. Particularly, we had some accidents in about 1954 with the Comet. The Comet was a commercial airline. We lost multiple of those over just a short period of time due to fatigue cracks that nucleated in given locations and failed. So we changed our methodology. We went to a fail-safe and then to a safe life design where we would build into the structure components that could take a crack and would have redundant structure in it, or say a strap where if a crack propagated into that, it would stop due to some different orientation of the structure. Well, we had some problems with that. In 1969, we had an F-111 that crashed down at Nellis Air Force Base at the range down there that only had a few hundred hours on the aircraft. It was designed for about, I want to say it was like 6,000 hours, and it only had a few thousand hours on it. And the wings ripped off of this airplane, and it buried itself in the Las Vegas desert. Well, come to find out, that was due to what we now call a rogue flaw. A large flaw in the wing attach fitting that failed and nucleated a fatigue crack, propagated the edge, and during a simple maneuver of that airplane, ripped the wings off the airplane. So we had to remodify our thinking. We had to do a paradigm shift. We changed to what is now known as damage tolerance. And damage tolerance manages aircraft with the idea that there is a rogue flaw. We can calibrate that size a couple different ways, whether it's new structure. We'll talk a little bit about that, but there's this idea of a rogue flaw in primary structure. So we've had this evolution to where we are now, and we currently work under a MIL standard. It's called MIL Standard 1530C, and that just came out recently in 2005. So we've had quite a history, and sad to say that oftentimes, I'm sure you guys are well aware, that failures seem to drive change, but we're doing pretty well, and we'll talk a little bit about how we apply this damage tolerance paradigm to what we do. So let's talk a little bit about linear elastic fracture mechanics. Linear elastic fracture mechanics, and then we'll start out talking a little bit about fatigue. So hit the next slide for me, Bob, if we can. You're clicking too fast. Oh no, you're on the right one. So let's talk a little bit about fatigue. Fatigue, it's important that we look at this. This is the definition from ASTM. It's a standard definition. It's important that we kind of look at a couple specific things about this definition. First, fatigue is a process. It's a process of progressive, localized damage in some structure that occurs because of fluctuating stresses or strains, and can result in either cracks nucleating and propagating, and can culminate in complete failure of the part. So it's important that we understand, one, that it's a process. It's not instantaneous. It's localized and progressive, and it's due to fluctuating strains and stresses. So it's something is being cycled, and we nucleate something locally, and we propagate it under these local strains and stresses. Okay? So in order to deal with fatigue in structures or in pipelines or anything, we use what's called linear elastic fracture mechanics for the vast majority of what we do. Linear elastic fracture mechanics uses a basic, simple model. In that model, it's kind of shown here on the right. It's an infinite plate in pure tension with a center crack in the middle of it. And we use a really, in my opinion, a really great equation. I'm not a fluids guy. I don't like partial differential equations. I like simple algebra. And this equation is pretty simple. It solves for something that's called a stress intensity. That stress intensity is a local property at the crack tip that correlates the far field stress and the crack size to determine if that given component will fail or not. So it's kind of like a yield strength or an ultimate strength, how that's a property. Well, there's a property of materials called fracture toughness, and it's related to this. So we can relate in a given structure, hey, it's got a crack this big in it, and if we get a load this big, will it fail or not? We do that by solving for this stress intensity. Okay, next slide. Now, I don't know about you guys in working the things that you, whether it's welding or ATK or F-16s, I don't work with infinite plates in pure tension. Is there anybody here that does? I'll come work for you because life gets, no? Okay, well, so what we have to do is we have to modify that basic model, right? We don't ever work in those things. So what we use is a beta correction. It's just a scalar multiplier that we tack onto the end of this simple equation that we can modify that basic model to adjust for things like geometric changes, whether we have, instead of an infinite plate with a center crack, say we got a hole, or we have an edge crack, or different things like that. We can modify that basic model to be able to adjust for that. Sorry, Kim. So what we're going to do is we're going to apply this beta correction. Remember, our title was beta correction. So we are trying to see in our research whether we can use this type of correction to adjust for some other principle. Next slide. So the United States Air Force's Structural Integrity Program. It's broken down into 3 main sections. Damage tolerance, which we use to manage our fleets of aircraft, is broken into 3 main sections. It's broken into fatigue crack growth analysis, then residual strength, which means if we have a crack that's this big and we hit this load, what's it going to do? So we need to calculate that. And then the final pillar of this is non-destructive inspection. We rely on our non-destructive inspectors to help us and work as a team with us so that we can manage these structures properly. And there's a whole range of ways that we do that, whether it's coming up with new inspections or whether it's going out and saying, hey, you know, this inspection technique's not working. Then we can say, okay, well, we're going to have to adjust the way that we do our fatigue crack growth analysis and residual strength to take into account your advice. Okay? Now, it's important that we understand that this has to be done in a closed loop process. We can't just work alone as structural engineers and think that, you know, everything's good and everything's great, and while our NDI guys are out in the field saying we can't find anything, we don't know what you're talking about, or we're finding huge cracks, and you start looking at this and we say, I don't know, we don't believe in cracks, there are no cracks. Well, we can't do that. We need to rely on them as a team player to understand what's going on in our structure so that we can do that. So it's a closed loop process. And it's important to understand that it's one of the main pillars of this. So what are some advantages of using damage tolerance to be able to sustain the structural integrity of our aircraft? Well, there are quite a few. One of the biggest ones is that we can begin to understand our materials. That's crucial for what we do as engineers. We need to understand the behavior of these materials, how they act, what does heat treating do to them, well, how do they behave under these given loads and strains and things like that. We can use linear elastic fracture mechanics. We can apply that simple equation to predict crack growth. That's really powerful. Then what are some other ones? Well, we can use non-destructive inspection. It's a requirement. It's not like, say, Safe Life, where we say, you know, this part will last forever, but if you have a chance, you're there, and stick a probe in that hole. Well, no. This requires us to include it into everything we do. Now, it's imperative that we as engineers work with our non-destructive inspection counterparts to understand some simple things about our structure when it comes to non-destructive inspection. There's 7 basic things. Okay, that's what to look for, where to look, how to look, when to look, how often to look. Those are 2 different things, and we'll talk about that. Then we can talk about probability of detection. If any of you guys were not here for Ward Rummel's presentation last time, you missed a great presentation, and I'm sure he'd be happy to give you that. He's got a lot of stuff on probability of detection. Then we need to understand detection threshold. What's the smallest crack you can find with some probability of detection? Then we can understand the failure modes that go into these structures and how they're going to react. Okay, so in the Air Force, we do this by a couple different ways. Calculations. Okay, that was part of one of those pillars. The other is that we identify fatigue critical locations on the airplane. Where on the airplane are we seeing cracks? Where do we expect to see cracks? Why are they cracking? How fast will they crack? We need to figure that out. It's not easy. It's not easy coming up with loading spectrum, coming up with loading profiles. How does a wing actually react when it's loaded? I don't know if you guys have recently flown in an airplane and looked out on the wing, but it's constantly vibrating out there. Well, we need to understand, well, what is it? How is it vibrating? How is it moving? What do those induce into the wing, and will things crack when we do that? And then we can develop inspection intervals. We can come up with NDI capability. We can apply different techniques to our structure. And then we can validate those things, whether it be through full-scale fatigue testing or whether it be through component testing that we'll talk about tonight. So we use these different things to finally develop, and that's in this corner, some fatigue crack growth curve. Your crack's going to get this big over this many hours, this many cycles. That's really powerful. Next slide. Now, I want to talk about 2 things, and this will be kind of important throughout the rest of the presentation. We manage our structure in 2 different ways, okay, when it comes to structural components. We have brand new structure, and we have sustainment structure, old structure, okay? When we have a brand new piece of structure, I don't know if any of you have heard of the F-22 Raptor or the F-35 Lightning II. That's a brand new airplane. When that brand new airplane comes off the lot, we develop some characteristic of the processes used to develop the structure of that airplane. And then we characterize that process to develop an initial flaw size down in that bottom left-hand corner. Okay, so Lockheed Martin, Boeing, anybody says, hey, we manufactured this spar cap using these techniques, and we've done inspection on these brand new parts, and we can guarantee 95, there is no flaw in those components over this size. We say, bang, okay, we're shooting with that. That's our new, quote-unquote, initial rogue flaw. And we develop a curve from that using some of the stuff I talked about, whether it be spectrum or anything like that. We take that and we divide it in half. And we can take, for our initial inspection, and we can take advantage of that whole crack growth curve. And then we just say our initial inspection for that is halfway between that initial rogue flaw and final failure. Well, when it comes to sustainment, and remember, in the Air Force, we really only have 2 brand new airplanes. So the vast majority of the airplanes that we deal with are in the sustainment world. We can't do that. We can only take advantage of, analytically, the fatigue crack growth life from where you, non-destructive inspection technicians and engineers, tell us is your detection threshold. We can only take advantage from that point on this curve to failure. We can't take advantage of anything before that. We have to manage from detection to failure. And that will become extremely important as Robert begins to talk to us a little bit later. Next slide. Okay, so this is a great slide. We do full-scale fatigue testing. This is currently going on. Dr. Mark Thompson, who couldn't be here tonight, is actually here in El Segundo. This is an A-10 fuselage that we have in a huge hangar that's hooked up to a gigantic full-scale fatigue machine where we are applying loads and strains to this fuselage, mirroring what it would see in real life and determining whether or not there are different locations on this fuselage that we need to begin to worry about. So we do, no kidding, we take a full airplane, stick it in a fixture, and cycle it like you would a component. And that's extremely important to us. We do it regularly because of how valuable it really is. Next slide. Okay, this slide basically shows us that during the application in about 1978 of damage tolerance into the way in which we manage our structure, we've been able to dramatically reduce the structural failures that we have in our airplanes. It really works. It's really beneficial. Next slide. Okay, let's talk a little bit about the introduction of this research. So Robert and I did our research on the change in crack growth characteristics due to a process called cold expansion. Now, the vast majority of the problem locations that we have on aircraft structures are at holes. We got lots of holes in airplanes that we put fasteners through. We have fuel going through them. We got all kinds of them. And you guys are probably really familiar with the idea of a stress concentration. That a hole, you have a stress concentration of 3. So you increase the stress just due to the presence of that hole by 3 times. So we have some real problems with holes. So one of the things that we do, one of the processes that we do to holes is that we cold expand them. And I'll just kind of use this as an example. We'll talk about this. So this has a hole in it. What we do is we take a mandrel and we shove it through this hole. Okay? Then we put a sleeve on that mandrel, and the diameter of the sleeve and the mandrel is greater than the diameter of the hole, the tip of this mandrel. It's tapered on the tip. Then what we do is we hydraulically pull that mandrel through this hole. And when we do that, we plastically expand the hole. And when you plastically expand a hole, all the other material around it freaks out. And it says, oh my gosh, I just got moved and I don't want to be moved. So it elastically tries to push back on that plastically deformed hole, and it squeezes it together. So it induces a residual compressive field around that hole. So it squeezes, if there is a crack that nucleates and begins to propagate in that hole, it squeezes that crack tip closed, or it does its best to do so depending on the load. So this process is cheap, it's efficient, and it's widely used in the aerospace industry and in almost any other industry that holes are a problem. It's just a great process. You get an extreme benefit in fatigue crack growth life. Okay, next slide. However, there are some problems in the United States Air Force with this. Like we talked about, the United States Air Force in the sustainment world, we're only able to take advantage of the point in which we can detect to failure. So what do we do in the Air Force to try and take advantage of this cold expansion process? We know it's extremely beneficial. We know there's some real benefits. So what do? Well, we're not exactly sure how beneficial it is. So what we do is, as we talked about, this initial flaw that you start out with in your analysis, you need, remember, K equals sigma square root of pi A, and A is crack size. You have to start out with some crack size, whether it's a nanometer or whether it's an inch. You have to start out with some. So we start out with some initial flaw size. And what the Air Force says is, well, cold expansion is really beneficial. We really like it. We're not really sure what to do about it. So what we're going to do is we'll reduce the initial flaw size. So we'll change it for, say, just for this example, and this is kind of a common example. We'll start from, we'll say instead of it being a 50 thou corner crack like you see in the corner here, we'll say we get some benefit, and we'll say it's roughly the equivalent of reducing that initial flaw size to, say, 5 thou. So you can see that there's a dramatic difference in the analysis of the crack growth life. Whether it goes from, say, like, 1,000 hours to something like 90,000 hours. Well, that's great. It's really awesome, except for the fact that we can only take advantage of in the sustainment world from where we can detect to where it fails. So instead of taking advantage of these first 8,500 hours, or 8,500, we can only take advantage from 82 to 11,000. So we got a big problem. We can't take advantage of all this. So what do we do about it? Well, we're going to try and work on something. And what we did in our research allows us to hopefully take better advantage of this. And I'll pass the microphone to Robert. We'll see if we can do this gracefully. And he'll talk to you about our research and then how we changed that, hopefully. Go ahead, Bob.
Do you want to pass out these
Sure.
to everybody? Did you hook this to your belt?
I did. I pushed it in my belt loop.
Oh, nice.
We'll pass some of our specimens around. If you could do us 2 favors. It's a real fun thing to put the fracture surfaces, to put them together. It's not real beneficial to the surfaces, though. And then if you could just not touch them with your fingers, or they're really sharp, so I wouldn't think you'd rub them on your face. But just don't put them together, but you can sure look at them, and we'll pass them around.
Yeah, I'll grab these ones real
I'll
quick.
pass them, Bob.
You got them? So, Scott has talked a lot about kind of background information. He's talked about, the Air Force, how we try and manage our structure. Kind of the main problems we have. Fatigue cracks are really what drive a lot of failures or a lot of retirements for aircraft. It's a pretty big problem, and one of the ways that we can try and extend the life of aircraft is this cold expansion process he's talked about. Fastener holes are a big problem. So the main issue we're faced with sustainment right now is the fact that we're trying to extend and extend and extend the life of these old aircraft because it's just way too expensive to make new ones. So we really have to get better at what we do as engineers and NDI techs. I mean, we're coming up with new inspection techniques all the time, but as engineers, we have to get better at understanding what's physically happening in our structures. So one of the ways we wanted to do that was to understand this cold expansion process and not just come up with some approximation, but try and physically model what was going on. So one of the driving factors, like Scott talked about, was this fact that the methodology we have right now really doesn't represent the physics. We wanted to actually be able to predict what's going on and not just kind of adjust one of the factors in our analysis. So we wanted to get our heads wrapped around the benefits of this process and be able to predict it. That's been the biggest struggle. Everybody understands that there's a lot of fatigue life benefit, but actually being able to pin down an analysis that you can use to predict that's the struggle. And so that's what we're trying to get to. So to do this, there's a lot of benefit. And we understood that, and so that's kind of why we invested some time into this research. Next slide. So what did we actually do? We've kind of done a number of things, talked about a number of things so far tonight. I want to talk about for a minute the research we actually did for our theses, and talk about some of the details, and then we'll get into results. And then at the end, I want to show a lot of pictures that I think will really relate to some of the things that you guys do. So what did we do? We did actual testing. The truth lies in the data, right? You understand, how it behaves. If you can simulate what's really going on, that's the truth, and that's what you're trying to get at. So we did fatigue testing. Now we picked 2 very, very different aluminum alloys, and we did that on purpose because we were trying to capture the overall spectra of how these things might fall out. Very different types of aluminums. And we chose aluminums because they're prolific throughout aircraft structures. They're all over the place, widely used in many different applications. So we chose a very high strength, low toughness material, a 7000 series, and we also chose a very high toughness, lower strength material in a 2000 series. Did a bunch of constant aptitude testing, and we did three different types of testing. One was to make sure that the data we were getting made sense. You know, this was the first time we had ever done any fatigue testing. We wanted to make sure that, you know, we weren't clear off in left field with our results, and, you know, we kind of matched data that we saw in the field. So we started with just some baseline ASTM specimens, and then we stepped up to, well, let's put a fastener hole in the middle. Let's try and model what a lot of our structure looks like. But let's start with something to establish a baseline. We needed something to compare to, and something that we really understood. So we really understand, you know, without this cold working process, how is this structure going to behave? We've got that pegged down pretty good. So we wanted to test that and see what the data told us. We needed something to compare to. And then obviously, we tested a lot of cold expanded specimens. That was our test case. We needed to understand, after we processed all these components, how did things change? And could we look at the difference between the two and use a beta correction like Scott talked about to try and capture that difference, and then roll that difference into our predictions so that we can predict the effects of this process. Slide. So here's just a picture of our setup. We did all of our testing up at Hill Air Force Base and Materials Lab. Appreciate them letting us use a lot of their equipment. It really was a lot of benefit. Slide. So, okay, great. We did all this testing. We got all this data, but you've got to be able to take it and get some value out of it. So we had to do some processing, and we had to understand several things that kind of cropped up throughout the testing. We had to try and look into that and understand how that affected the overall differences that you saw as a result of this process. And one of the things that I think is really going to be important from the NDI community, and that's what I'm going to talk about in a minute and show a bunch of pictures. But one of the things that really jumped up, and it actually was a little more than we expected, it was a little more difference from the standard specimen that we expected, was the actual shape of the cracks. I don't know if you deal with fatigue, typically what you see, and you know, it's going to kind of vary a little bit, but typically what you'll see is a crack will start, you know, at a fastener hole. It'll start out in the corner, and you'll have a nice corner crack, and it'll transition, and it'll stay fairly symmetric, and then it'll go straight and propagate through the specimen. Well, that isn't what this looks like. This is a cold expanded specimen, and you can see this kind of unique P-shaped crack front, is I guess how we call it. And it's very odd, and it can really cause a lot of problems if you're developing an inspection, or if you're an NDI guy and you go out and say, you know, I want to inspect a spar cap in a wing box, and I don't want to take the fastener out, I just want to do a surface scan inspection, you know, because say I've got a whole row of fasteners that I want to look at, so if I got to pull out all those fasteners, it's going to be a lot of work. But if I just do a surface scan, you know, that's great. Maybe I can see a crack that's acceptable, and it's a lot easier inspection. Well, the problem is, what if I'm inspecting this side of the hole? I may not see the crack. I might not truly understand how big the crack is. It may be on the order of, you know, half an inch on the other side, and you can't even see it on this side. So I'll talk a little more about that. But that's one of the things we ran across that's very important. And I think that's one of the reasons why Ward asked us to come talk today, is just talk about, you know, getting people thinking about, you know, it's not so straightforward. It's not just a nice, simple corner crack, symmetric, propagating through components, and it, you know, it's really idealized. It's not what happens. So you need to understand how your processes affect everything that's going on, whether it's your inspections, your fatigue life, different things like that. So next slide. So we understood that. We did some marker banding. We looked at how does the crack shape change as this crack's propagating through the component. We got that nailed down, and then we had to take that data and get to something useful. And Scott talked about a stress intensity, and that's the way that we can compare the two on an even baseline, look at a standard specimen and look at a cold worked specimen, and really relate the two and see what is the difference from this process. Can we pull something out and figure out, you know, really what am I getting? What's the advantage I'm getting from this process? So we needed to get a distress intensity. Well, we had to put together finite element models to understand for our given component, our given loading, our given crack shapes, what was the stress intensity as a function of crack size. So that's kind of how we worked through to understand this stress intensity versus crack size for all these different components we tested. Slide. So once we understood that, we had to come up with some beta correction. We had to understand, can we capture this benefit in terms of a beta correction? It's kind of a different way to look at it, but from a sustainment point of view, it's a great way to handle it. So how did we do that? Well, it's all based on similitude principle, which really says for a given crack growth rate, if I have two components that are exactly the same, for a given crack growth rate, at that crack tip, the stress intensity is the same. So if you see the crack propagating at the same rate, the stress intensity at that crack tip is exactly the same. That's the similitude principle. And based on that, we can compare the two and pull out a beta. So we understood, for every single specimen, we understood the crack growth rate versus crack length. We got that from our test data. We also understood crack growth rate versus delta K. We got that from our test data and from our FEM models. So from that, you can calculate this difference as a result of that process. So if you go to the next slide, Scott, I think it's a little, this is kind of another slide to another spin at it, another way to view it. So really, what I've got here is I've got crack growth rate versus stress intensity. And this curve is actually my baseline. That's what I would expect from just a standard specimen, open hole, no cold working process. And this is well established. We've got a lot of data, and that's fairly consistent. So that's kind of what I'm comparing to. But what if I process these? What about all my cold expanded specimens? How does that change? And what you see, this is one example of one specimen. You see this shift. And that shift is an artifact of this process. So you've actually shifted the data, and the only thing that's causing that difference is that actual process. That's the only thing different between these specimens. And that's an artifact of cold expansion. And so based on that, at a given crack growth rate, you can compare these two and you can calculate a beta correction for cold expansion. Well, you guys are probably wondering, what does that matter to me? Well, the next slide kind of talks about that. Next two slides. So this is our results. There's a couple things I want to talk about. Now, if you remember, I said we picked two very different aluminum alloys. We did that on purpose because we wanted to, we were kind of limited because we realized this was two thesis research projects. So I mean, not a lot of money, low budget. We were trying to do what we could. But we figured, let's pick two very different aluminums that we use a lot and see the differences. But one thing I want to say is the overwhelming majority of the fatigue life is for the small crack sizes. So down in this area is where you spend a large amount of the actual fatigue crack growth life is spent in those small crack sizes. So out here, this is small potatoes compared to the rest. Not so important. This is important. And one thing I want to show is there's really not a lot of difference between the two. All of us were expecting a lot more difference, and we didn't really see that. So that's actually a good thing, because maybe there's not as much variability as we thought. One of the, a lot of the criticisms of doing something like this is, there's just way too much variability. It ain't gonna work. Think of all the things that, different configurations, different materials. Well, maybe it's not as much variability as we think as far as what this process is doing. But if we can understand the effects and understand this, then maybe we can take advantage of it and help ourselves. So if you go to the next slide. So really, this is the money shot, as Paul likes to say. He's the owner of the money shot. This is the shot that really management cares about. This is what everybody cares about. Stress intensities, betas, corrections, that may go right over your head and no one really even cares about that. But this is actually where the rubber hits the road. This is what's important. So I want to kind of walk through this plot because it's pretty important. So clear off here to the left, the squares, that's just a standard specimen. So what we're looking at is we're looking at crack length. This is the important axis. This is life. So this is how long something's going to last. This is how quickly it's going to fail. Okay? So all the way over here on the left, you look at these squares. That's just your normal component, no cold working process. Say you've got a fastener hole in a skin. That's your prediction. You can see it's on the order of less than 20,000 hours, maybe 10,000 hours. But these three solid curves, so the triangles, the circles, and the squares, that's actual test data that we had. Our mean, our minimum, and our maximum life results from our testing. That's actual data on the benefit that you saw from this process. Now everybody, you know, that is familiar with this understands there's a benefit, but I mean, the shortest one is about 450,000 cycles versus, you know, 12,000 cycles. So for our given testing, for our given situation, there was a dramatic benefit from that process. So we understand, if we can understand this and predict it analytically, there's a lot we can gain in not having to re-inspect aircraft as often. I mean, because that's very expensive to have to take airplanes apart, pull out fasteners, do inspections. So we're trying to get away from that by understanding what's physically going on. Now, the diamonds is the Air Force's current methodology to take advantage of that process. So look at the difference on what we're currently predicting, and look, we're clear over here. This is really what's going on. This is physically how long it takes to fracture. So there's a lot to gain. But then you look, the X's are actually predictions from our derived beta corrections. So there's two important things I want to bring up, and we'll zoom in a little bit and talk about kind of this little area. But there's two things I want to talk about. One, look how much better the actual life prediction is. You know, we can get a lot better in the ballpark of what's really going on with a methodology like this versus just reducing the initial flaw size. But the other thing that's very important when you start talking about NDI, you start talking about sustaining aging aircraft. You remember, we have to manage from what we can detect to what is critical, not from some assumed initial flaw size. NDI comes into play and is very important. With our current approach, we're really limited because we assume the crack's really small and it stays small, and then all of a sudden it goes fast. Just based on the overall model and reducing the initial flaw size, you don't get a lot of benefit. So really, even though there's 400 and something thousand cycles of life in this component, based on our current methodology, we show 15,600 hours that, based on analysis, that's how long it's going to last from our detectable flaw size to critical. So really, we're stuck in this little teeny box. This is how we have to inspect. We got to keep bringing it back to the depot, keep bringing these jets back, keep taking them apart, and continue to do inspections, just because we don't really understand what's going on as far as being able to predict the crack growth. However, if we can come up with a beta correction that actually predicts the physical crack growth, can model the crack shape and the total life, I mean, we're clear off over here. We're not even on the screen. I mean, the life is so long, it's not even on the screen. And the nice thing about it is, because of the behavior of the cracks at cold expanded holes, it's kind of unique because the maximum residual stress is kind of a little bit away from the hole. The free edge is no stress. So you've got to get into the component a little bit for you to really feel the effects. So what happens is the crack actually starts to propagate similar to what you would see in a normal specimen, but then it hits this area of high residual stress and kind of just shuts down for a long time. So that's good from an NDI point of view because it's at a detectable flaw size for a long time. That's pretty important. So the crack shape is important. How the actual behavior is going to, how this specimen is going to behave is very important. So there's a lot of implications to that. So this is kind of the money shot. Next slide. So I want to talk about crack growth shape and how it relates to NDI and different inspections, and go through a lot of pictures just to talk about a lot of things. Now, we passed around some specimens. I've got a bunch of pictures on here. So really what you're looking at is we've had specimens, you know, that cracked, felled. We've broken them apart, and these are the two fracture surfaces. You see in these pictures, those are the two fracture surfaces laying on top of each other, and you're looking at that fracture surface. And there's a couple things that I really want to talk about that I think really affect NDI. The first is I've got just some E647 specimens that we tested, and I've got non-cold work specimens. And the one thing I really want to talk about is the morphology of the fracture surface. They're very flat, not a lot of features, typical of what you would expect. There's not a lot going on. I passed, you know, some non-cold works around and some cold work specimens around. You can see there's not a lot going on. It's pretty flat, and you see this, typically you see this nice symmetric corner crack transition to a through crack. So it fits fairly close with how we're trying to model things. Next slide. And so here's some more pictures. You guys have seen this, but there's not a lot going on. These are some more non-cold work specimens. Will we go to the next slide? So I want to bring this back up again because this is pretty important, I think, from an NDI perspective. Scott talked about this process. Now, one of the selling points for cold expansion is it's a one-side application. So you don't have to crawl. If you think about it, and you think about the wing of a plane, there's kind of some little access points. You can get inside the plane and work on it, but it's really cumbersome. It's really difficult to do. So the great selling point about this process, you don't have to get inside the wing. You can just stick the mandrel in, have the sleeve on, and you can pull it from the outside, and you can cold work it. That was the big selling point for this. Big deal. But there's some problems with that. Not necessarily problems, but there's things you have to think about when you do that. And really what this does by this process is not just a simple two-dimensional residual stress field. It varies depending on how it was processed. So what happens is, because of how the material flows and how you pull that mandrel through, the residual stress on this side of the component is different than you see on this side. It's a three-dimensional residual stress field. And really what that means is the cracks are going to grow differently on this side than they do on this side, and that's important. So if we go to the next slide. So the reason why that's important, we talked about this P-shaped crack, and I showed that marker band specimen that showed how the crack propagated through the specimen. Well, depending on your inspection, it's not just this nice, neat, symmetric corner crack or through crack anymore. You might have a very small crack on one side and a very large crack on the other. So for example, the first thing I want to talk about, just to kind of orient you guys, this is a specimen here, and it actually failed on this side, but you can see this is how big the crack was on the other side when it failed. So you have this nice P-shaped crack front. This is the side of the specimen that they started pulling the mandrel through, and this is where it exited. So they, if you think of just this half, they pulled the top, they pulled the mandrel through that direction. So you have lower residual stress on this side and higher on this side. Now, kind of the crazy thing, and I'll show some more pictures here in a couple slides, is in our testing we saw crack lengths on this side on the order of less than 1/10 of an inch, very small. Sometimes 5 thou, 10 thou, 100 thou, but pretty small relative to the crack sizes on the other side. So really what we had is we had a crack that was almost catastrophic. It was to the point where it almost went critical, but you could barely see it on this side. So what if I'm doing an inspection on this side, I don't want to remove the fastener and I want to do a surface scan right here? I never see it. I never see the crack. I can't see it because it's hidden under the fastener head. But it may be clear out here on the other side. It may be almost catastrophic, but I'll never see it. So it's just something to think about. We need to be careful. We have great processes, but we need to understand what we're doing to our materials when we're doing these processes, and make sure we're covering our bases, making sure we have the right inspections, just make sure that we're understanding what's going on. Next slide. So the other thing I wanted to talk about, and I've got some really cool pictures coming up, but this really unique kind of tearing area, and this is an artifact of that really high residual stress that I was talking about. So you have this area on the exit side of the specimen that the residual stress is so high that the crack just doesn't want to propagate through that area. So what we actually saw in our testing is these cracks would start to grow right here in the EDM notch, and they would grow, and they'd hit this little area right over here, and they'd say, yeah, I'm not going to propagate through there, I'm going to go all the way around. So we would have cracks growing around this whole area, and you'd have a little crack show right here, you'd have nothing right here, you'd have a little crack pop through clear over here, and then all of a sudden this would just fracture. So it would completely grow around that high residual stress area, and then finally it just got to the point where it couldn't take it anymore. But that could be a problem where really just below the surface a little bit you might have a crack clear out here, but you can't see it on the surface. So it's something to keep in mind. Next slide. So here's just another picture, kind of what I've talked about, just from a different perspective. This is just a standard specimen. You can see the crack's nice and open, and you can see it with this visually. But the other thing that residual stress is doing is it's closing your crack. So it's really squeezing your crack down. So that could have some pretty significant NDI implications also. Slide. I'm going to step through a handful of pictures I got from FDI, Scott and I did, and from Coakley, and they kind of highlight how these crack shapes change as an artifact of thickness of your specimen. So the thickness of your component is pretty important. So the next two slides, these are both half-inch thick specimens, and you can see there's this really really explicit type of P shape and some really unique crack fronts. But what you see, these are non-cold work specimens, nice, neat corner cracks that you see in the components. You've got these just really odd crack shapes that you really need to, I guess, think about, get in your mind when we start thinking about what type of NDI inspections we want to do. Next slide. So this is also half-inch non-cold work specimens. This is typically what you would expect in a component that's just a standard hole. But then, I mean, think about this specimen right here. This was actually fracture. You never even saw the crack on this side and it went catastrophic. But look how long it is over here relative to thickness. So because of that high residual stress over here, the crack didn't even propagate through thickness. It just headed this direction. Path of least resistance, right? So we're going to go to some thinner specimens, half-inch. So kind of the trend I wanted to highlight was the fact that the thinner and thinner you got, the less of difference that you saw between these two specimens. You didn't really see this really crazy crack front shape. It kind of fell more in line with the non-cold work specimen. So you see here's a 1/4 inch, and it's not as big of a difference. And then if you go to the next slide, 0.63, and then really there's not too much of a difference when you start talking about thin sheet. So that's things to keep in mind, especially you start thinking about thick specimens or thick components. You may really have a big effect and things you need to think about with your crack shape. Next slide. So these are some of the pictures, some of the crazy cracks we saw in our testing. What really happened is we had about a 1/10 inch crack right here on this side. We're looking at the exit side. And then we had this crack growing out over here too. None of this was here. None of this was here. So we had this little teeny crack, and then it grew all the way around, and it was starting to grow out here. It was really crazy. And then all of a sudden, one cycle, this thing just popped. So these residual stresses can be a pretty big player in how the crack's going to behave. And this just highlights what I already talked about. You may hide what's really going on with fasteners and different things like that. So you need to think about this and decide if you need to do bolt hole eddy current inspections or surface scans, different things like that. Slide. So one of the things, I don't know, I think some of you know Ward Fong. We work with him quite a bit at Hill. He's kind of our point of contact for NDI. And we worked together, and we were really concerned about, we do a lot of bolt hole eddy current inspections on the A-10 and different aircraft. And we were really concerned that, is this unique crack front shape, is that residual stress closing the crack, are all these things coming together to change our probability detection and our detection threshold if the hole is cold worked? What is the effect? So what we're going to do is we've got a bunch of specimens we're going to test. We're going to run them for a bit so that we grow a certain size crack in them, and then we're going to hand them over to Ward. And he's going to take them. He's going to do some NDI inspections. He's going to tell us, well, this is what size cracks you have. These are the indications I have for some baseline and for some cold expanded specimens. And then we're going to break them. And we're going to see, how far off is he from the truth? Is he spot on? What are the effects of this cold expansion process? So that's kind of some follow-on research we're going to do, just as an artifact of what we saw in our original testing. So what's the impact of this? Well, sustainment is big money. I mean, we're taxpayers. We're spending an awful lot of money for military purposes, and sustaining old aircraft is very expensive. So Scott and I were trying to come up with a process to get better at what we do, sharpen the pencil, become better engineers. So really, what's driving all the costs? A lot of depot inspections, taking things apart, looking at them, doing inspections. It's driving a lot of costs. And a lot of these are just a handful of locations that are driving those costs. There's a couple locations that are really, really critical, and they're really, shortening how often we have to bring the aircraft back. So it's really driving a lot of costs. But a lot of these locations are cold expanded holes. So if we can understand this process, we can take advantage of it. So just as an example, if we could increase our inspection intervals by 15%. Now realize, if you remember the curve, the life benefit you know, it was like 450,000 cycles versus, you know, 20,000 cycles. So that's a dramatic difference. If we only can take advantage, just a small increase, 15%, the A10 weapon system alone can save the taxpayers $20 million a year, every single year. Just by understanding this process, increasing our inspection intervals by 15%, that's a lot of money. We're not bringing planes back. Aircraft are in the air flying like they're supposed to be and not down, taken apart. So that's really why we did our research. So just to walk through conclusions, we want to understand the effects of cold expansion. We realized there were shortcomings in some of the approaches we have right now. We realized maybe there's a pretty big impact on NDI when it comes to the crack growth behavior and the shape of the crack front. But we knew there was a lot of fatigue life benefit, and we just needed to be able to capture it analytically. And we plan on doing some follow-on research to understand the implications for NDI. That's it. Questions?
Yes. So your beta correction basically says that, I mean, it's intuitive that if you put a compressive load into it, that you're going to stop your crack. But your beta correction is really showing that as a material problem, right? And it's showing that you're reducing the stress intensity at the crack tip. Is that what I?
Yeah, that's great.
It's a way. It's a engineering approach to capture the reduced stress intensity at the crack tip.
And so now that you've shown that as a material property, then you can push out the NDI because you pushed out.
Well, we're modeling what's physically happening. It's a nice thing. And so instead of this reduced initial velocity approach, we're modeling what's physically happening, so we don't have to reduce our initial velocity. So based on just how it behaves, the NDI problem goes away from a sustained point of view. It goes away because we don't have to assume some reduced initial velocity. We just start it like we do all of other sector.
And the current practice would be, we know that there's a crack there, so we have to inspect it.
We have to assume there's a crack because we have to.
Doing cold work, right? So you knew that there was a crack there to begin with.
Well, no, not necessarily. We do it just to get the fatigue benefit here. We know we have certain areas that are hot spots, that are problems. Some things are cold worked right out of production because they're undercost technique to really get a lot of bang for a low cost. So it's done all over the place. I mean, the commercial industry has been doing this, and the military has been doing this process for 30 years or more. I mean, it's been around for a long time. It's just people are struggling to pin down analytically what the benefit is, and that is the struggle. Everybody understands that there's a lot of benefit. It's being able to predict it reliably so that you can take advantage of it. That's the problem. So right now, so far, it's been kind of a safety factor in a way, where we need to sharpen the pencil, get better at what we do, and understand these processes and what they're doing to our components, and be able to predict it.
Yeah, go ahead.
How does the fastener change this model? Did you look at that?
We did not. That's a really good question to say, like, how does a bearing load from a fastener change the characteristics in the crack growth behavior? We did not. That's a factor that's really big. And another factor that someone might ask is the idea of spectrum loading. We're just doing constant amplitude loading. What happens if it's not that? That's something, like Robert said, with kind of the limited time and money that we had in our research, we didn't do. But that's definitely one of the follow-on things that we'd like to do, because very rarely do we have critical locations that are cold work and they don't have a fastener bearing on the hole. So that's a really good question. But it would change.
We wanted to focus on something
Seeing if it
simple.
worked.
Start from something simple and see if we can understand it, and then you can use that to leapfrog to some of these other things.
So your next step might involve the loads put on those flaws that are.
Sure, make a joint.
Yeah.
Yeah.
And see if that, if they had a certain fastener with a certain load on it, that would even extend the life longer.
Yeah, that's a really good question.
How do you monitor the crack lengths if they were cracked?
Oh, that's a really good question. Let me see if I can back up a couple slides. We used traveling microscopes. It's too bad Ward Fong isn't here. Actually, you can see one right here. Because he's trying to buy us some new ones. But there's a picture of one. And let me show you. So what we did is we put a traveling microscope on a mount, and Dr. Jones and Dr. Clark spent many hours looking
Through those
at
things.
cracks. Well, they use different things, but they use those as well. But you take a microscope and you mount it to a machine. You see them right here. We built a little fixture, mirror rod, mounted them to this machine, and so they would traverse over the front and back, so both sides of that crack. And then on the back, in order to monitor the crack length through the bore, we would tilt it at a given angle, and then we would measure the bore length using it and calculate the angle at which we were doing it, and so we could use just some, as my dad says, everything comes down to Pythagorean, so we would use the Pythagorean theorem, and we would figure out how long the crack was. But we measured it using traveling microscopes, so we didn't do like clip gauges or any type of other technique. We straight up used some University of Utah.
We wanted more accuracy. We wanted to understand not just the overall, because a lot of other techniques give you kind of loss of area and stuff like that. We want to understand how is the crack growing on this surface, how is it growing through the bore, and how is it growing along the back surface, so we could really understand that crack front shape.
Did you measure the events?
Yes.
every time?
Yeah.
How
Well,
did you measure that?
we schwagged it.
What do you mean measure events?
Every time
We
you can
did
have a bunch of cycles going, you won't have an event, so the crack's not going. But then you'll have an event when the crack starts growing.
Well, we followed E647 standard as far as measuring how often to take measurements.
But it kind of gives some guidelines, and sometimes it would grow faster, so you'd want to measure, say, instead of at 20,000 cycles, you would want to measure it at, we want to make sure that we get every 50 thou crack growth
I'm
increments.
doing this on purpose because I'm trying to sell you excuses with that.
Oh. You have to talk to the board for me. Good question, though. Any others? Okay. Well, thank you for having us. Again, we're grateful for the opportunity to be here. Where are those specimens at?
They're right here.
Great. Thanks. Thanks, Steve. Thank you again. If you have any questions that you don't want to ask,